In the previous video, I showed you how to find the volume of a solid by slicing. There are some very special volumes called volumes of revolution that involve the same technique. So let's consider a function f of x on the interval from a to b, shown in blue below. And now we're going to take the region that's bounded by x equals a, x equals b, y equals 0, and y equals f of x, and we're going to revolve it around the x-axis. So you can imagine spinning this region around the x-axis, and that is going to give you a solid. Let me draw that solid for you right now. So I'm going to reflect this curve about the x-axis, and imagine that I've spun the curve around the x-axis so that you get kind of a circular shape to that curve. And I want to find the volume of this solid. Now, this abstract picture that I've shown you may seem like it's not important, but one example that I can show you is if I took a line and I revolved it around the x-axis, the resulting solid is a cone. And so that's a great way to figure out what the volume of a cone is. Okay. So what I'm going to do is I'm going to slice the solid into vertical discs of thickness delta x. So you can imagine that I can slice through the solid and I can make a series of thin vertical discs, just like I had done before with the volume of the pyramid. Now the thickness of these discs is going to be delta x. But each one of these discs has a radius, and we'll call that radius, say, r sub I. So, what is the volume of each one of those disks? Well, it's going to be pi times r sub I squared times delta x. But what is r sub I? Well, in fact, it's located at the point x sub I, and that radius is in fact f of x sub I. So we get that the volume of that disk is going to be pi times f of x sub I squared delta x. So that's the volume of one disk. We're going to want to sum them up. So we're going to do the sum from I equals 1 to n pi times f of x sub I squared delta x. Now, if we let delta x go to 0, that's the same thing as letting the number of disks go to infinity. Again, we're thinking here about delta x as being b minus a over n. Then the volume of the solid is actually an integral because this is a Riemann sum. And that integral goes from a to b, and then pi times f of x squared dx. And now we can evaluate that integral to find the volume of a solid of revolution. And so this formula for this specific kind of example will come up over and over again. So let's do one of these. Let's consider the region in the first quadrant bounded by y equals 4 minus x squared. So the first thing that I'm going to want to do is I'm going to want to draw this region. It's the region in the first quadrant, and it's bounded by the parabola 4 minus x squared. So I'm going to revolve it around the axis so that I get this solid of revolution. So the volume is going to be pi times the integral from 0 to 2, because those are the x values that are involved, of 4 minus x squared. That's the function, which represents the radius. It gets squared, and then I'm integrating dx. So this is pi times the integral from 0 to 2. I'm going to square this out, so I'm going to get 16 minus 8x squared plus x to the fourth dx. And so that's going to give me pi times 16x minus 8 thirds x cubed plus 1/5 x to the fifth, evaluated between 0 and 2. So that's pi times 32 minus 64 thirds plus 1/5. And I will leave it to you to figure out that exact value for the volume of revolution. So this is a pretty standard example. I would like to do a couple more examples. This first one is going to be the volume of revolution about a different axis. So we don't have to revolve necessarily about the x-axis. So I'm going to find the volume of the region that's bounded by e to the minus x. X equals -1. So I'm going to make this -1. X equals 0. And y equals 1. So this is y equals 1. Now I'm going to plot what e to the minus x looks like. This is e to the minus x. And then I want to revolve it around the region y equals 1. So in fact, I'm going to make this solid right here. Okay. So I want to proceed in the same way that I did before. I want to slice into disks. So I'm going to slice this solid into disks of radius r. That disk appears at x sub I. It has a radius I'll call r sub I. And so what is the radius of that disk? Well, it's not just the height of the function. It is the height of the function e to the x minus 1. And so the volume of one of those disks is going to be pi times e to the minus x minus 1 squared. So pi times the radius squared times the thickness delta x. So now I imagine that I'm going to sum up the volumes of these disks, and I'm going to make them thinner and thinner so that this becomes an integral. So the integral in this case for the volume is going to be the integral of pi times e to the minus x minus 1 squared dx. And then we have to think about what the x range is. The x range goes from -1 to 0 in this case. So this integral is going to be from -1 to 0. Okay, so again, I think that this integral is going to be easier if I square everything out. So e to the minus x times e to the minus x is e to the minus 2x. And then minus 2 e to the minus x and plus 1 dx. So this becomes pi times minus 1/2 e to the minus 2x plus 2e to the minus x plus x evaluated between -1 and 0. So this becomes pi times minus 1/2 e to the 0 plus 2e to the 0 plus 0 minus -1/2 e to the 2, because I'm plugging a -1 there, plus 2e to the first power minus 1. So I'm going to get pi times, let's see, I've got a 1/2 e squared. I have minus 2e. So the 1/2 e squared is there. The minus 2e is there. And then finally, what's left is my 2e to the 0 minus 1/2 gives me 3/2, and then plus 1 is going to give me 5/2. And so this becomes plus 5/2. And if someone needed it, you could find a decimal approximation. Okay, so let's do one more example. And we want to find the volume of revolution. This time, instead of about the x-axis, we're going to do it about the y-axis. And this example is going to have two important new concepts in it. One is that we're going to rotate our function around the y-axis. And then the other is that the region is going to be formed by two curves. Those two curves are going to be x cubed and square root of x. So we're going to rotate this around the y-axis now. And what that does is it makes this interesting kind of bowl shape. So I'm going to imagine that I've essentially have a big bowl created by x cubed, right? And then I've taken out the red piece that you see there. So maybe I'll show these together. Okay. So I'm going to slice this horizontally. So by slicing this horizontally, then instead of having dx's, I'm going to have dy's. So I'm going to use a method, and that method, when I slice this horizontally, is called the washer method. Essentially, if I slice through this horizontally, then what I'm going to get is I'm going to get a thin disk. And that thin disk has an outer radius, which I'm going to call RO. But as I'm slicing through, I'm also seeing a smaller disk on the inside. And that smaller disk has a radius RI. And so I'm kind of boring out this thinner disk from, or this smaller disk from the larger disk. And so that's making a washer. So you can imagine that if I slice this horizontally, that I'm going to end up with a series of washers. The thickness here is going to be delta Y. So I'm imagining everything's going to be in terms of Y. So I'm going to take functions like Y equals X cubed, and I'm going to want to think about it as X being in terms of Y. So I'm going to take the function Y equals the square root of X, and I'm going to think about it as X being in terms of Y. That way, the outer radius is going to be this type of distance. And so that's the distance to the curve Y equals X cubed. So the outer radius is going to be Y to the 1/3. And then the inner radius, which is this distance, that's the distance to Y equals square root of X. So that's going to be R sub I equals Y squared. So the volume of one of these washers is really going to be the volume of the outer cylinder, pi times Y to the 1/3 squared minus pi times Y squared squared. So we're taking the outer radius, the outer cylinder volume, and then we're subtracting the inner volume. Okay, so that's the volume of each one of these washers. Of course, we're going to add up an infinite number of these washers so that the volume of the solid is actually the integral of pi times Y to the 2/3 minus Y to the 4th dy. Now the limits of integration, okay, are going to be the Y values here. They go from 0 to where these two curves intersect. These two curves intersect here at 1, 1. So Y is going to go from 0 to 1. Okay, all that's left now is to find the integral. So we're going to do pi times Y to the 2/3. The antiderivative is 3/5 Y to the 5/3 minus, and then we're going to do 1/5 Y to the 5th, that for the Y to the 4th antiderivative, and we're going to evaluate from 0 to 1. So this is actually going to be pi times 3/5 minus 1/5. So the volume of this solid is actually 2/5 pi. And so now you've seen what happens when we choose to rotate around a different axis, in this case the y-axis, but also when our solid is bounded by two curves, and so instead of thin disks as our cross sections, we're going to have thin washers.